18 days. Just 18 days after Starship Flight 12 left the launch pad, SpaceX was already ready for the next flight. Not a few months, not a full year like before, just a few more weeks. Booster 20 just completed its cryogenic pressure test. Ship 40 is having its engines installed. The launch pad looks as though no rocket has ever lifted off from it. 221 days. That was the gap between Flight 11 and Flight 12. This time, that number could drop to under 30. So when will Flight 13 actually fly? And why is it happening this fast? Fast enough to seem almost unbelievable. Stay with us. The answer will surprise you. The system architecture has changed at a fundamental level. Starship Block 2, the version that flew before Flight 12, had a brain that operated like a decision tree. You pre-programmed it. If situation A occurs, do B. If C occurs, do D. Finite branches. The system was very good at handling situations that had been anticipated in advance. But when an unanticipated situation arose, the system had no branch to follow. Block 3 is different. Its brain doesn't run on a decision tree. It runs on real-time re-optimization, continuously recalculating every millisecond based on the actual state of the vehicle at that moment. Think of it this way. Old generation GPS. You make a wrong turn. It takes a few seconds to recalculate, then gives you a new route from where you are. New generation GPS. It adjusts continuously the moment you begin to turn, before you've even finished the turn. No gap, no moment of being lost. Block 3 is new generation GPS, but instead of navigating a car, it is navigating a rocket moving at 17,000 miles per hour through an environment of temperatures reaching thousands of degrees Celsius. And this is where Flight 12 left behind real evidence. When Ship 39 lost a Raptor vacuum engine 36 seconds after stage separation, no one at SpaceX headquarters in Hawthorne was hand-flying that vehicle. No engineer was sitting at a keyboard typing in correction commands. The system recalculated on its own, immediately. It extended the burn of the remaining 5 engines. It adjusted the re-entry trajectory in real time. The heading indicator on the live stream display showed continuous yaw correction inputs throughout the entire descent. Not a momentary stabilization, but sustained active guidance work throughout. Ship 39 landed on target in the Indian Ocean. 1 engine failed. The system compensated. The vehicle came home to the right spot. This is proof that the architecture works as designed. It is precisely because Block 3 has this capability that SpaceX can prepare Flight 13 faster. The reason? When the system is smart enough to handle many unexpected situations on its own, engineers don't have to sit down and analyze, how do we prevent this from happening again? They only need to understand why the engine shut down, then fix that root cause. Everything else, the system already handled. But does real-time re-optimization have limits? What happens when the number of simultaneous failures exceeds the system's capacity to compensate? The answer to that question will come from Flight 14, not Flight 13. And that is precisely why Flight 13 needs to happen first. 39 minutes. The number no one put in the headline. 39 minutes. That is how long SpaceX takes to fully load propellant into Starship 5-3 before launch. A vehicle standing 407 feet tall, taller than a 40-story building, carrying more propellant than any rocket in the history of humanity has ever loaded in a single fill. 39 minutes. Let's compare it to another rocket. NASA's Space Launch System, SLS, the most powerful rocket NASA has ever built, begins propellant loading approximately 10 hours before launch. The main loading sequence takes 5 to 6 hours. Then an additional 4 hours of continuous top-off to compensate for propellant that boils off. Total, 10 hours, for less propellant than Starship 5-3. So how does SpaceX do it in 39 minutes? The answer is simple enough to be almost funny. 2 quick disconnects. 2 separate connection interfaces at the base of the booster. One for liquid oxygen, one for liquid methane. Instead of loading sequentially through a single point, V3 loads in parallel through 2 points simultaneously. Imagine you need to fill 2 enormous swimming pools. The old way, one hose. Fill this pool, then move to the other. The new way, two hoses, both pools at the same time. SpaceX didn't pump faster. They opened a second pumping line. This is not just a technical achievement. This is the economics of rocket launching. When a rocket is sitting on the launch pad, it isn't doing anything. The pad is locked. No other rocket can use it. Every hour on the pad is a cost. Operating costs, opportunity costs, the cost of everything else that has to wait. SLS needs 10 hours on the pad just to load propellant. Starship needs 39 minutes. If SpaceX wants to launch Starship multiple times per month, their long-term goal is dozens of flights per year, then 39 minutes is one of the most important puzzle pieces in the entire picture. Could 39 minutes be cut down to 20? Some engineers argue that with 3 connection points instead of 2, that number is entirely achievable. If so, the math of the entire program changes once again. But 39 minutes is only one of 3 numbers Flight 12 left behind. And the second number, related to the heat shield, will change the way you think about the entire future of crewed missions. The heat shield endured what it was never designed to endure. 3 minutes after Ship 39 separated from Booster 19, a Raptor vacuum engine shut down. The trajectory deviated. SpaceX decided to skip the planned Raptor relight in space. Reduce risk, play it safe. A reasonable call. But that decision carried a physical consequence that nobody stated clearly during the broadcast. The header tank, the auxiliary propellant tank located in the nose section of the vehicle, still had propellant inside it when re-entry began. What does that mean? Every simulation of how heat distributes across the vehicle's surface during re-entry was calculated based on one foundational assumption: standard mass distribution. Light nose, heavier base. When the header tank was still full, the nose of the vehicle was heavier than designed. The center of mass shifted forward. The angle of attack upon hitting the atmosphere changed. Heat distributed across the hull surface in a pattern that no prior simulation had ever calculated. Ship 39 entered re-entry under conditions the heat shield had never been designed or tested to withstand. And the heat shield held. Not a single tile burned through. In aerospace engineering, when a system handles more stress than it was designed to bear, that is called a safety margin. That is not luck. That is evidence that the design has matured to the point where it has a buffer zone beyond its official specifications. For the first time, Starship's heat shield showed that signal clearly. SpaceX had mounted multiple different tile test groups on the same vehicle, different adhesives, different attachment methods, and let all of them go through the same re-entry conditions simultaneously. No lab, no CFD simulation can recreate 1,500 degrees Celsius plasma with sufficient precision to support real engineering decisions. SpaceX collected comparative data from multiple configurations in a single flight. One flight. Multiple parallel answers. And then, there were the 2 satellites. Among the 22 objects Ship 39 deployed from its payload bay, 20 were mass simulators. Metal blocks shaped like Starlink satellites to test the deployment system. The remaining 2 were actual Starlink V3 satellites, with antennas, thrusters, independent control systems, and imaging equipment. After deployment, Ship 39 executed a maneuver. It turned back so that those 2 satellites could scan the entire heat shield surface before re-entry began. Autonomously. No crew required. No space station required. No special conditions required. Compare this to the space shuttle after the Columbia disaster in 2003. NASA developed the rendezvous pitch maneuver, a procedure in which the shuttle would flip near the ISS so that crew members aboard the station could photograph its belly. That procedure required the ISS, the correct lighting angle, crew members seated at the right windows in the right positions, and a specialized approach trajectory. Not every mission could perform it. Starship requires none of that, on any orbit, at any point in the flight. NASA will never certify Starship for crewed missions to the Moon or Mars without a verified method of inspecting the heat shield before re-entry. That is a hard post-Columbia requirement, non-negotiable. Flight 12 just demonstrated the first version of that capability. But SpaceX has not yet released the images from those 2 Starlink V3 satellites. Why? There are 2 possibilities. 1, The resolution is not yet sufficient for NASA to accept it for the certification process. 2. The data is being analyzed, and SpaceX is waiting until it has enough information before publishing anything. Both mean the same thing for Flight 13. If SpaceX releases those images, that is a signal the capability is matured enough to show NASA. That is a step toward crew certification. If no images are released, the autonomous heat shield inspection story is still in the internal analysis phase. That is one of 4 things to watch when Flight 13 happens. But before getting there, you need to understand a larger picture. Because Flight 13 does not serve just one objective. It serves 3 clocks running simultaneously. 3 clocks are running, and Flight 13 must serve all 3. There is a way of looking at Flight 13 that most followers of the program don't use, not as a single test flight, but as an intersection node. A point where 3 completely different pressures from 3 completely different directions are converging at the same moment. Clock 1, Artemis. NASA, Artemis. 3. The mission to return humans to the surface of the moon for the first time in more than 50 years is targeting 2028. Starship is the human landing system for that mission. Without a sufficiently reliable Starship, there is no Artemis 3. Before Starship can land astronauts on the moon, SpaceX must demonstrate orbital propellant transfer, refueling between 2 starships in orbit. The reason? A Starship launched to Earth orbit does not carry enough propellant to fly directly to the moon. It must be refueled by a tanker Starship already in orbit before it can make the trip. No one has ever transferred cryogenic propellant between 2 spacecraft at this scale in a microgravity environment. The behavior of cryogenic liquids under microgravity conditions cannot be fully predicted by simulation. You have to actually do it. And NASA will not authorize orbital propellant transfer testing until Starship has demonstrated sufficient reliability on an orbital trajectory. Every unresolved failure mode from Flight 12 is a step backward in the Artemis timeline, not because NASA wants to obstruct, but because there will be astronauts on board, and those astronauts need to come home. Clock 2. Starlink Thought 5. 3. SpaceX has announced that Starlink 5.3 deployment will begin in the second half of 2026. A single Starship can carry 60 Starlink 5.3 satellites per flight, compared to 24 Starlink 5.2 on a Falcon 9. That number is an economically decisive difference, not just more. Cheaper per satellite, faster per deployment batch. But that economics only holds when Starship flies frequently enough and reliably enough to support actual scheduled deployment timelines. A Starship with failure modes not yet fully understood on an orbital trajectory is not a foundation on which to build a business plan around 60 satellites per flight. Flight 13 is the first step in building that track record. Clock 3. IPO. SpaceX has filed IPO paperwork. In the S1 filing, they explicitly stated that their growth strategy depends on the ability to increase launch cadence and payload capacity, both of which depend directly on Starship. Investors will read every Starship flight as a signal about the company's trajectory. A Starship stranded in an uncontrolled orbit right before the IPO is a headline that nobody at SpaceX wants to stand in front of Wall Street to explain. This is why SpaceX will almost certainly not exercise the FCC orbital permit for Flight 13, even though they already have it in hand. To be precise, when SpaceX filed with the FCC and classified Ship 40 as orbital, that was not a commitment. That was a special temporary authority, a maximum authorization. You are permitted to do up to that much. It does not mean you will do everything that authorization allows. This is a ceiling, not a floor. The evidence is already there. Flight 10 and Flight 11 both filed as orbital, both stopped at suborbital. SpaceX looks at the data from the flight and decides, not at the permit. Now, if Flight 13 executes perfectly, boostback successful, engines stable, no new failure modes, could SpaceX decide to push to orbital right there in Flight 13? Who holds the authority to make that call? And would they dare do it with 3 other clocks already running? Those are questions without answers yet. But to understand why Flight 13 is such an important intermediate step, you need to understand one technical problem that very few people explain correctly. Boostback. Why this is a problem of predictability, not reliability. After Flight 12, many people asked the same question. Has SpaceX fixed the boostback failure? When will they finally catch the booster? Right question, but looking at the wrong problem. The issue is not just reliability, whether the system can perform correctly. The deeper issue is predictability. Whether you know in advance when that system will perform correctly under specific conditions. Think of an old car that sometimes starts and sometimes doesn't. When it does start, it runs fine. Reliability while operating is acceptable. But you don't know which morning it will start. Predictability is poor. You cannot make plans around that car. A catch attempt with Mechazilla doesn't just need a reliable booster. It needs a predictable booster. For the chopsticks on the tower to catch the booster must come back to exactly one point in space with accuracy measured in meters. Not tens of meters, meters. The entire sequence of boostback burn and landing burn must execute correctly in terms of thrust level, timing, and angle. Not just in the right direction, but correct on every single parameter. If the boostback burn fails in an unpredictable way, the booster could land hundreds of kilometers from its target. Could be less, could be more. You don't know in advance. And when you don't know where the booster is going to come down, you cannot position the chopsticks in a ready-to-catch stance. Because if the booster doesn't come back to the right spot and you have already extended the chopsticks, you are placing the entire launch tower, the entire ground infrastructure worth hundreds of millions of dollars in potential danger. No responsible engineer would do that. This is why Flight 13, truly, needs to accomplish something specific, not catch the booster, but prove that the Block 3 booster can successfully execute a boostback burn in actual flight with Raptor 3. With the higher separation velocity of Block 3. With the full real-world post-separation dynamics, not in simulation, not in a static fire, in flight. Booster 19 could not ignite enough engines for the boostback burn. The result? It came down approximately 300 kilometers from its Gulf of Mexico target. Everything downstream, the landing burn, the catch attempt, became impossible not because those steps failed, but because the first step had already gone wrong. If Booster 20 in Flight 13 successfully executes a full boostback burn, that is a more important milestone than any catch attempt. Because it establishes the foundation of predictability, the prerequisite condition that every subsequent catch attempt depends on. A simple analogy. Before you trust that a driver can stop a car on the exact line in the rain, you need to see them do it at least once. Not to stop right then, but to know that it is possible and to begin building data on when it succeeds and when it doesn't. One successful execution. That is the threshold. Everything else comes after. But while the story of SpaceX's speed and engineering is unfolding, on the other side of the industry, a competitor just went through something no one in the business wants to witness. And the way SpaceX is responding to that says more than any official announcement. Blue Origin and the lesson of single point of failure. The story of the explosion at LC-36 has been told many times. Vehicle lost, launch pad damaged, lightning tower down, fire burning for hours. But there is one question few people asked after that explosion. Why did Blue Origin have no backup plan? This is not a question of criticism. This is a question of architecture. Blue Origin built New Glenn according to a philosophy. Build it right, build it once, build it to last. Invest deeply in each component. Don't replace what doesn't yet need replacing. Operate safely, step by step. That philosophy is not wrong on a technical level. It is the philosophy that put humans on the moon in 1969. Saturn V was built with that same mindset. But it has one very specific vulnerability in the new era. When something breaks, you have nothing left to continue with. No backup launch pad. No hardware designed for rapid replacement. A single path forward. And when that path is blocked, everything stops. LC-36 was New Glenn's only launch pad. It was destroyed. New Glenn was grounded entirely. And here is the detail that most people don't analyze correctly. When CEO Dave Limp announced that Blue Origin would not rebuild the transporter erector, the vehicle transport and erection system that was completely destroyed, but would instead transition to direct vertical integration on the launch pad like SpaceX, that was not a decision made in response to the explosion. That was a decision Blue Origin already had in its plans. The explosion simply eliminated the transition cost, the cost that, when the system was still operational, no one wanted to pay. This is a pattern that has appeared repeatedly throughout the history of aerospace engineering. After the Columbia disaster, NASA redesigned the external tank attachment process. Improvements that engineers had known were necessary for years beforehand, but that no one wanted to implement while the system was still flying. The disaster created a window to fix what operational pressure had been preventing for years. Blue Origin is in that window right now. The question is how they use it and how fast. CEO Dave Limp announced that Blue Origin will fly again before the end of 2026. That is the official target. But NASA Administrator Jared Isaacman, who personally visited LC-36 after the explosion, suggested 2028 as a more realistic milestone. A 2-year gap between the CEO and the largest customer is not a technical disagreement. It is a signal about the level of confidence in the timeline. And NASA has begun suggesting that the Blue Moon lunar lander, the mission New Glenn was designed to carry, may need an alternative plan. Not contract cancellation, just a suggestion about a backup plan. A suggestion like that from the head of NASA does not carry the weight of an ordinary suggestion. Meanwhile, what is SpaceX doing with all of this? They are continuing in exactly the same direction. Not slowing down, not adjusting their timeline, and not because they have no problems, but because the way they built the system from the beginning means that a single problem cannot bring everything to a halt. Pad 2 is operational. Pad 1 is being constructed in parallel. If Pad 2 goes down for any reason, Pad 1 continues. If Pad 1 has an issue, Pad 2 is still there. This is not a luxury. This is a design for the worst-case scenario. But even with all of those advantages, something is happening hundreds of kilometers from Starbase, aboard the ISS, that many people are not putting in its proper context. The ISS, when today's problem creates tomorrow's pressure. The International Space Station is leaking air, not for the first time. And this time, seriously enough for Mission Control to order 5 of the 7 crew members to put on their spacesuits and withdraw to the Crew Dragon docked at the port. Not an evacuation, but not routine either. The leak area is the PRK, the short connecting tunnel between the Zvezda module and the aft docking port of the station. This problem began in September 2019. Initially, only 90 grams of air per day, small enough not to be concerning. But it grew. By April 2024, the leak rate had peaked at 1,678 grams per day. NASA's Office of Inspector General, the independent auditing body, published a report identifying 4 actual cracks and 50 areas of concern. On NASA's internal risk matrix, the PRK area scored at the maximum on both axes. Highest probability, most severe consequences. The highest risk anywhere on the station, ever. Roscosmos wanted to fix it in the most practical way. Cut away the covering panels, access the cracks, patch them. NASA calculated that the cutting process could turn a small, slow-leaking crack into a large, rapidly depressurizing breach. They did not say no to the repair. They said, measure more carefully first, then cut. 2 hours after the withdrawal order, Roscosmos agreed to stop. The crew returned to normal operations. This is what everyone already knew. Here is what few people are placing in its proper context. The ISS is scheduled for decommission in 2030. That is 4 years from now. And within those 4 years, the next generation of commercial space stations needs to be ready to take over the ISS's role in low Earth orbit. Starship is the planned transportation vehicle for the modules of those stations. Without a sufficiently reliable Starship, there is no firm timeline for the commercial stations. Without the commercial stations arriving on time, the gap between ISS decommission and the next station extends longer than planned. The ISS incident is not just a problem of a 25-year-old space station aging out. It is direct pressure on Starship's schedule. Because the more signs emerge that the ISS is approaching its operational limits sooner than planned, the greater the pressure on Starship to be ready. The question no one has dared to answer directly: if the ISS has to end its mission before 2030 for technical reasons, could Starship be called in as an emergency transitional solution? And if called, would it be ready? That is a question Flight 13 cannot answer on its own. But it is one piece in that larger picture. When Flight 13 happens, the live stream will focus on what looks the most impressive: the flames, the noise, the moment the chopsticks extend or don't. But if you want to genuinely understand where that flight sits within the larger picture, here are 4 things to watch, and why each one matters more than any catch attempt. First, Booster 20's boostback burn. This is the single most important KPI of the entire flight. Not whether the catch happens, whether the boostback burn succeeds. Full burn, correct parameters, no early abort. If Booster 20 accomplishes that, SpaceX has confirmed they understood the failure mode of Booster 19 and fixed it. That is the foundation of predictability. That is the prerequisite for every subsequent catch attempt. If Booster 20 has problems with the boostback burn again, it means the failure mode runs deeper than the initial analysis indicated. The catch attempt timeline for Booster 21 will have to wait at least one more flight for verification. Second, Raptor 3 stability on Ship 40. Ship 40 will be the second time Raptor 3 has flown on the upper stage. Flight 12 was the first, and one engine shut down. If Flight 13 completes the ascent phase without an engine failure on the ship, that is an important data point. The Ship 39 failure was an isolated incident, not a systemic issue with the Raptor 3 design. The question of orbital trajectory will be opened up more seriously for Flight 14. If there is another engine failure on Ship 40, the investigation must go deeper into the Raptor 3 design. And orbital trajectory continues to be deferred until the answer is clear. 2 flights are not enough to draw definitive conclusions, but 2 consecutive flights without failure will begin building a pattern. Third, in-space relight test. Flight 12 skipped this test because the trajectory deviated after the engine failure. If Flight 13 includes an in-space Raptor relight in the flight plan, that is a signal SpaceX is confident enough in the overall flight to add new complexity. If that test succeeds, it is a direct step toward deorbit capability, a prerequisite of any orbital mission. If Flight 13 does not include that test, SpaceX is still in a conservative phase. Validate what is already known before adding what is not yet known. Not a bad signal. Simply a confirmation that the program is moving methodically. Fourth, does SpaceX release the images from the 2 Starlink Vi-3 satellites from Flight 12? Not during Flight 13, before Flight 13. If SpaceX publishes the heat shield scan images from Flight 12 before Flight 13 takes place, that is a signal the capability has matured enough to show NASA. That is a step toward crew certification. If no images are published, the autonomous heat shield inspection story is still in the internal analysis phase. All 4 of those data points combined will tell you where Flight 13 stands in the longer journey, not just as the next flight, but as the first brick in the execution phase that SpaceX has been building toward for years. Flight 13 is not the destination. It is the open door, and what passes through that door will determine the pace of everything that follows. Flight 13 is not just the next flight. It is the first test of the execution phase, the moment where years of preparation get measured against real data. Thank you for analyzing this with the Space Brief today. If this perspective was valuable, like, share, and subscribe. Tap the end screen right now.